Section 2.1, Definition 2, Right Triangle Trigonometry. This section has 3 objectives. We are going to first start with Objective A. Find the 6 trigonometric functions of an angle given the sides of a right triangle. In Chapter 1, we learned the definition for the 6 trigonometric functions for any angle in standard position. Now we'll learn the second definition for the 6 trigonometric functions in terms of the sides and angles in a right triangle. Definition 2 states, if triangle ABC is a right triangle with C equaling 90 degrees, then the 6 trigonometric functions for A are defined as follows. Sine A equals the side opposite A over the hypotenuse. So that would be A over C. A is the side opposite of angle A, and C is the hypotenuse. Cosine A equals the side adjacent A over the hypotenuse. So the side adjacent to A is B, and the hypotenuse again is C. Tan of A equals the side opposite A over the side adjacent A, so that would be A over B. Cotangent A equals the side adjacent A over the side adjacent, or opposite A, my apologies, which equals B over A. Secant A equals the hypotenuse over the side adjacent A, which is C over B, and cosecant A equals the hypotenuse over side opposite A, which is C over A. Note that the side A, lowercase a, is the side opposite angle A, but it's also adjacent to angle B. And the side lowercase b is the side opposite angle B, and it's adjacent to angle A. Okay, so depending on the perspective at which you're looking at the length, it can either be the side opposite a specific angle or adjacent to an angle. Let's do our first example. Triangle ABC is a right triangle with C equaling 90 degrees. If A equals 12 and C equals 15, find the 6 trigonometric functions of A. So here we're given the name of our triangle, which is ABC. So let's draw a triangle A, B, C, and this triangle we know is a right triangle with C equaling 90 degrees. So we then know our lengths as A, B, C, and that's lowercase c. Okay, we know A equals 12. We know C equals 15, and we need to find the 6 trigonometric functions, so all 6 of the trigonometric functions. But before we do that, we need to find the length of side B. So we'll use the Pythagorean theorem to help us do that. A squared plus B squared equals C squared. So we'll substitute 12 for A. We're trying to find B. Substitute 15 for C. So I'm going to get B squared by itself. So I will be subtracting 12 squared to the other side. I then will take the square root, and so I will get the square root of 225 minus 144, which will be the square root of 81, which equals 9. We're going to take the positive 9 because length must always be positive. And so now I know B equals 9. So A equals 12, B equals 9, and C equals 15. So using those three values, I can find the 6 trigonometric functions of A. So we're looking at A as our angle perspective. So the sine of A will be the side opposite A, which will be lowercase a, which is 12, and the hypotenuse, which is 15. So if we simplify that, we would get 4 over 5. The cosine of A is the side adjacent A, which is B, which is 9, over the hypotenuse, which is 15. And so that would equal 3 over 5. The tan of A is the side opposite A, which is lowercase a, which is 12, over the side adjacent A, which is B, which is 9, and that simplifies to 4 over 3. Then we have the cotangent of A. So that's the side adjacent A, which is 9, over the side opposite A, which is 12, and that's 3 over 4. Then we have the secant A, which is the hypotenuse, over the side adjacent A, which is B, so that's 9. So that's 5 over 3. And then we have the cosecant of A, which is the hypotenuse over the side opposite A, which is 12. So that simplifies to 5 over 3. And then this would be our answer for the 6 trigonometric functions of A. Okay. We've just worked through an example using our new definition of trigonometric functions. So now let's compare it to definition 1 from section 1.3. In section 1.3, we were told or introduced to definition number 1, which is shown here in figure 3a. In this section, we are now introduced into definition 2, which is shown in figure 3b. Okay. Note the similarities between definition 1 and definition 2. Now, both definitions work fine if angle A is acute, meaning between 0 and 90 degrees. But here's the catch. Definition 2 only applies to acute angles because it's based on a right triangle, and right triangles can only have acute angles. Okay? Whereas in definition 1, okay, theta could be any angle, acute or not acute. Okay, so it makes definition 1 more valuable because it can handle any angle, not just acute ones. Okay, so let's head to objective 2 before diving further into definition 2. Our second objective is objective B. Find trigonometric functions using the cofunction theorem. So some trigonometric functions are naturally paired together in what we call cofunctions. These pairs are related because each function complements the other in a special way. Sine and cosine are cofunctions. Tangent and cotangent are cofunctions. Secant and cosecant are cofunctions. So now let's apply this to definition 2 with the triangle ABC. So let's use triangle ABC to show the cofunction relationships. So in figure 4, if we are looking from the perspective of angle A to the side length lowercase a, we would see here that lowercase a is the side opposite A, but it's also the side that's adjacent to B. Okay, so looking at the first example here, sine B is going to equal the side opposite B over the hypotenuse. Now the side opposite B is lowercase b and over the hypotenuse c, which is equal to the cosine of A. Well, the cosine of A, although not shown here, is the side adjacent, the cosine of A is the side adjacent to A over the hypotenuse. Well, the sine adjacent to A is also the same side that's opposite B over the hypotenuse. So that would be B over C. And this cofunction relationship is very similar to all of the remaining 5 cofunction relationships. Okay. So these relationships can be summarized using the following theorem. The cofunction theorem states that a trigonometric function of an angle is always equal to the cofunction of the complement of the angle. Remember, two angles are complementary if their sum is 90 degrees. So if x is an acute angle, then its complement is 90 degrees minus x. According to the cofunction theorem, the following relationships hold for any acute angle x. Sine x equals cosine 90 degrees minus x. Cosine x will then equal the sine 90 degrees minus x. So each of the cofunction relationships will be similar. Tan x equals cotangent 90 minus x, but then cotangent x would equal tan 90 minus x. Secant x equals cosecant 90 minus x, and cosecant x equals secant 90 minus x. So this means that each function is equal to the cofunction of its complementary angle. For example, if you know the sine of an angle, you automatically know the cosine of its complement, and vice versa. This connection is a powerful tool when solving trigonometric problems. So in our first example here, let's fill in the blanks so that each expression becomes a true statement. So we are asked to find the sine of what degree measure equals the cosine of 60 degrees. Okay, well, the cosine of 60 degrees equals the sine of 90 minus 60, which is the sine of 30. So this would be 30 degrees. Tan 65 degrees equals the cotangent of what degree? Well, tan and cotangent are cofunctions. So the tan of 65 degrees equals the cotangent of 90 minus 65, which simplifies to the cotangent of 25 degrees. Okay. The secant, I believe this is supposed to be secant. There we go. The secant of x equals the cosecant of what expression? Well, secant and cosecant are cofunctions. So the secant of x is going to equal the cosecant of 90 minus x. We can't simplify that expression, so it will be 90 minus x degrees. Okay. All right, let's head into our last objective, which is to simplify trigonometric expressions using a table of exact values. If we were asked to calculate the sine, cosine, and tangent for special angles mentioned in section 1.1, so that would be the 30-60-90 or the 45-45-90 special triangles, we arrive at the results shown in this table. This is referred to as a table of exact values to distinguish it from a table of approximate values, which we'll explore later in this chapter. So the 30, 45, and 60 degrees over the sine, cosine, tangent, we then have our exact values. So the sine of 30 degrees would be 1/2. The sine of 45 degrees would be 1 over the square root of 2, or if simplified further, would be square root 2 over 2, and then so on and so forth. And we can use this table of exact values to help us solve trigonometric problems. So in our first exercise here, we're asked to use the exact values to show that the following statements are true. So they just want us to show that these statements are true. So the first one, it says sine squared 60 degrees plus cosine squared of 60 degrees equals 1. Well, sine of 60 degrees is the square root of 3 over 2. And the cosine of 60 degrees is 1/2. Okay, so if we were to simplify this, we would get 3 over 4 plus 1 over 4, which equals 4 over 4, which equals 1. And that's true. Our next one, sine squared 45 degrees plus cosine squared 45 degrees equals 1. So the sine of 45 degrees is the square root 2 over 2. And the cosine of 45 degrees is also square root 2 over 2. So if we were to simplify these, let's simplify them first. If we were to simplify these, we would get 2 over 4 plus 2 over 4, which equals 4 over 4, which equals 1. And that is correct. In our next exercise, we are asked to let x equals 60 degrees and y equal 45 degrees in each of the following expressions, and then simplify each expression as much as possible. So 3 sine x. So here x equals 60 degrees. So 3 sine 60 degrees of 60 degrees. Well, the sine of 60 degrees is the square root 3 over 2. So if we were to simplify this further, we would have 3 square root 3 over 2 as our final answer. The next one, cosine 2y. So the cosine of 2 times y, which is 45. Well, the cosine of 45 is 90. Or the cosine of 245 is 90 degrees. And the cosine of 90 is 0. Now that is not on our exact values chart. However, if we were to draw our coordinate plane and identify values on our terminal ends that lie on the axis. This is y, x. This would be the point 1, 0. This will be the point 0, 1. This will be the point -1, 0. And this will be the point 0, -1. All of these have an r of 1, or a distance from the origin of 1. Okay, so if we were to look at 90 degrees, which would be right here on the y-axis, all right, so this would be 90 degrees. Okay, this would be our x and our y, and cosine is going to be our x over our r, so that would be 0 over 1, because r is 1 here, and 0 over 1 is just 0. Okay. Next, 5 times the sine 3x, and x is 60, minus 90. So that would be 5 times the sine of 180 degrees minus 90. So 5 sine of 90 degrees. This is similar to the last one. So the sine is y over r. So if we go back to our 90 degrees, r is 1, y is 1. So y over r is 1 over 1. So that'll be 5 times 1, which is 5. Okay. Alrighty. Awesome.